How's it going, guys? This is Kelly Cox, and today we're going to go over the Collatz conjecture, and we're going to start with the basics. Starting information, we're going to look at any positive whole number. If it's odd, we're going to multiply by 3 and add 1. If it's even, we're going to divide by 2. And all the odd numbers are going to give us even numbers, so we can do them in 2 steps. 3n plus 1 divided by 2. And there are a couple other formulas that can accomplish this same thing. The first one is one I use to give me positions. I don't even really use this anymore, but it is a cool formula to have in my pocket. And then there's this one, n plus 1 divided by 2, which means we're going to take half of the number and add it to itself. And then if we want to go in the reverse direction, we would do n minus 1 divided by 3. And we can do this on all 1 mod 3 even numbers. A couple of things that you need to understand is that when you divide an even number, you will eventually run out of zeros and find an odd number. And the same is true for the ones in the remainder side of a number, and that is that you will eventually find an even number. So once you hit a 1 mod 4 number, the next result of this formula will give you an even number. And just an interesting fact that once you find the even number, the next number, which would be 3 steps below, will be below the number that you use the formula on. And then all 3 mod 8s go to a 1 mod 4 number. And all 7 mod 8s go to 3 mod 8s. Only odd numbers that are 5 mod 8 are able to get to the number 1 as their next odd number. So 5 goes to 16, 8, 4, 2, 1. And then we'll talk a lot about the loop. And 1 is only 1 mod 8 that can get to 1. I like to say it this way: the question that's being asked here is, can you divide an odd number in half? And the answer is yes. By using 3n plus 1 divided by 2, you have divided the number in half. That's why you have a 4 to 1 loop, because you can't divide 2 to the power of 1 in half. So anytime you get to a 0 or just 1 as the remainder, you can't divide those. So with 0 we get undefined, and with 1 we get 4. So when we divide 1 in half, the result is 4 because it cannot be divided. And now we'll dig into the details. All right, again, here's the formula that creates an interesting result with all odd numbers. And just a reminder that when we do the above formula, you're removing a 1 from the right side, the remainder side of the number, when we're looking at the binary, and it's an odd number. There's a remainder side and a power side for that number. And what we're doing is we're taking a 1 from the remainder side and moving it to the power side. And then, right, with this formula, we're doing 2 steps. Right, we're doing a multiple of the number, 3n plus 1, and then dividing by 2. But with every odd number, as we increment up, the difference between where we started and where we end is a numerical 1 through infinity, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Every odd number is the next difference to all the numbers that we use, right? So you can take any number and find it by taking an odd number and multiplying it by 3, add 1, divide by 2, and you can find any number from 1 to infinity. And then I like to show the wheel, and I color code all of my numbers by their mod 8. So if they're 1 mod 8, they're yellow, 3 mod 8 green, 5 mod 8 blue, and 7 mod 8 will be red. And like I said, only 5 mod 8s can get you to the number 1. And so I'm circling the odd numbers that are the next step is the number 1. And again, the only one that is not blue that can get you there is 1. And it loops because it's a 1 mod 8 number. All right, so now I want to talk a lot about the binary part of numbers. So the 2 formulas that are basically tied to this conjecture are we're going to divide by 2, multiply by 3, and add 1. So the interesting thing to me about that is that they're all built upon each other. So if we take, right, if we switch to binary and adding and subtracting, when we take 2n, we're basically taking the number and adding itself and getting the results of that. So in binary, right, we're adding the number itself to get that 2 times n. So with 3, what we do is we take the binary and copy it and then push it all to the left 1 spot, right? So we add a 0 to the end. Or we're taking the results of 2n and adding it to the number itself. Right? And then with 3n plus 1, we're taking the results of 3n and adding it to itself. So all of these build upon each other, right? And they all deal with just the last three parts of a binary number. So everything we're doing, I mean, there's a lot of noise happening above the first three numbers of binary, but nothing above these first three have an impact on what is happening with this conjecture in the grander scale of things. So that gives us 8 possible results when we're looking at a mod 8 of a number. So we have 7 mod 8, 3 mod 8, 1 mod 8, and 5 mod 8. And if you go up a level in mod, right, so here I go to mod 16, I take 3 mod 8 and I change it to mod 16, it splits half of those numbers, right? Half of 3 mod 8s are 11 mod 8s, and half of them are, remain true 3 mod 16s, right? And all 3 mod 16s go to 5 mod 8. All 11 mod 16s go to 1 mod 8s, and we'll dig into this more later on, but I just want you to keep, right, there is a path that each number has to follow, right? And then there are 4 even numbers that you can have, and we're going to divide by 2 with all those. But on the odd side, 7 mod 8 is going to go to 3 mod 8, and 3 mod 8 is going to go to one of the 1 mod 4s. Right? So the next thing I want to talk about is finding the correct power of a number. And we do that by just looking at the binary of that number, and we read from right to left. The first group of 1s is the remainder. The first 0 after the group of 1s is our power position. And so in this example, the third slot is our power position, which means we are in a power position of 8 times 1 plus 2, or 8x plus 2, or 2 mod 8, right? So if we mod the number 10, we get 2 mod 8. So everything to the left is the power of the number, and everything to the right is the remainder. Anytime you multiply a 4x plus 3, so a 3 mod 4 number, you're dividing a 1 from that number and moving it to the left side of the number. So if you take the number 3, multiply it by 3x plus 1, you get 10. All right, so we took the number 3 and we multiplied it by 3x plus 1. So we took 2 ones on the, right, here is our power. So we have 2 ones on the right. After we multiply by 3 and add 1, we took one of those numbers and moved it to the left side of the power. Right? Then we divide by 2. So on the right, we multiply 3, add 1, divide by 2. We now have divided our power in half. Right? We went from 8 to 4. Right? Our power position moved down one spot, but our power number remains the same on the divide by 2. Right? All we're doing is cutting our power in half. So we went from slot 3 to slot 2, and we divide, right? We're removing a 0 from the remainder side, so our remainder is divided in half. And so now I want to look at a few other examples. We're going to constrain ourselves to 8 bits of a number for this example. Right, so our max number would be 8 ones. So we can start with 8 zeros and go to 8 ones. All right, but we're going to look at the number itself, what it looks like in binary, and then what its power number looks like. So here we have the number 8. So our power position is in the 5th slot. So that gives us 32 times, there's nothing to the left, so that's times 0 plus 8. So our whole number is 8 mod 32. Now, if I multiply, well, we're going to divide it in half because it's an even number. And so what happens is our power number doesn't change even though we took a 0 from the right and moved it to the left side of the power number. Right? But our power position dropped from 5 to 4, so now we're at 4 mod 16. We have right, we've cut our remainder in half and we've cut our power in half, but our power number didn't change. So now I'm going to put a 1 in front of the power position. So now we've added 3 to the power side, and if we divide that in half, we get 52. So see, we still moved a 0 from the remainder to the power side, but it goes past the power number, right? So it's remained 3 and didn't go to 6, right? So our power slot moved from 5 to 4, so we're at 16. Our remainder went to half of what it was, but our power number doesn't get changed. If I take 52 and multiply it by 2, right? I'm taking a 0 from the power side and giving it to the remainder side. And so I've moved my power from 4 to 5, right? I doubled it from 16 to 32. I doubled my remainder from 4 to 8, but my power number doesn't change. So what happens if I modify my power number or my position, right? Let's move it to the 4 slot and look at what happens, right? I've moved my power slot from 5 to 4, same number, right? My power position is 1 less, so I go from 32 to 16. I've doubled, right? I'm adding a 0 to my power number, so I've doubled it, right? So it's 3 times 2, right? And my remainder remains the same, because if there's a 1 in the power slot, it's part of the remainder, right? The 0 in that slot is the dividing, but the 1, if there's a 1 sitting in that power position, it's part of the remainder. Let's move it down to the 3rd position. So here we didn't add a 0, we added a 1. So our number went from 6, right? We went 2 times 6 is 12, and we added 1. So anytime we take a 1 from the remainder and move it to the power side, it's done as a multiple of whatever we're doing. So in this case, we're doubling the number, so times 2 plus 1. So anytime we take a remainder from our remainder side and move it to the power side, we do a multiple of whatever we're doing, and then we add 1 to it, right? So we're going to, in this case, double it and then add 1. So our power slot is 3, so we divided that in half. Our remainder went from 8 to 0 because we took the power, that 1, and moved it to the other side, right? So now let's look at odd numbers. So here we have the number 7. We're going to multiply it by 3. I want you to see what happens here. So we multiply 7 by 3, we get 21. We took a 1 from the remainder side and moved it to the power side. So we do not change the power position, right? Our power position didn't change, but we took 0, we multiplied it by 3, and then we added 1. And so that gives us a result of 1. And our remainder, we lose a 1, and so we lose 2 spots, right, in our remainder. And then when we add the 1, we add back 1 to the remainder. So we take the last 2 spots and we flip them, right? So we go from 0, 1 to 1, 0. So the add 1, right, only happens on the remainder side. It doesn't affect the power side of the number. But we did a 3x plus 1 to the power side when we did just the multiple of 3. And then when we add 1, we're only modifying the remainder side of that number. Right? So let's reload. So, right? So we're back to 7. and we're going to give it a power, right? So now we have 23, right? So we have a 1 in the power side and the same setup on our remainder side. And we're going to multiply it by 3 again. We get 69. And what happened to our power side, right? We added a 0. Well, we multiplied 1 by 3 and added 1. So what happened? We went from 1 to 4 on our power side. Our remainder side, again, we lost a 1 and gave it to the power side. And so now I want to look at, right, 7 is a 7 mod 8, and so now we're looking at a 3 mod 8 that has a 1 on the power side. So we multiply this by 3, we get 33. And with 3 mod 8 numbers, we can, both slot 2 and 3 will be zeros when we multiply by 3. So I'm going to hold my power position in the same for those type of numbers to allow us to see what's happening. Because when we do the two-step process, it will be at the third slot. So if I add 1 to it, it's going to move the power position back to the third slot. But you can see that by holding it there, I took 11, made it 33. On my power side, I took 1, multiplied it by 3, and added 1, and got 4. And I lost 2 from my remainder side. And since this 33 is a 1 mod 4 number, I'm just going to multiply it by 3. So anytime you have a 1 mod 4 number, a 1 mod 4 cannot you cannot take the last 1 and move it to the power side, right? The multiply by 3 doesn't work in that scenario. So it just adds a 1 to the remainder side. So it pushes our power, right, from slot 2 to slot 3. But I want you to see that when we take a 1 mod 8 number, or 1 mod 4, and we multiply by 3, since we didn't move a 1 from, right, when we add that 1, it stays on the remainder side. So 4 times 3 is 12, right? We added a 1 to our power side, but in a way that it's only multiplied by 3 because we didn't add a 1 at the end of the number. And then if we take, right, we multiplied 33 by 3 and we add 1, we still do not change the power of that number. the one that we added stays on the remainder side. So we went from 1 to 3 to 4, right? And we cut our power number in half and doubled our power position, right? We went from slot 2 to slot 3 to slot 4. And so any 1 mod 8 number is going to have this characteristic. We're going to take the power from slot 2 to slot 3 to slot 4, and then we're going to do our loop, right? 4 2 1. And so we're going to look at some numbers and look at the correct power of those numbers later on. But this is what it will look like. It'll be, show us the step that we're at, the number, what its mod 8 is, what it looks like in binary, and then the correct power, what the power number is, and the remainder. And then I'm going to show you what's happening from an X perspective. And then some other ways we can divide an odd number in half, right? If I take the number 3 and I add 1, I get 4. I can then divide it by 2 and then subtract the 1 that I had, right? And I've divided 3 in half, right? So if I take 7, I add 1, I get 8. Take 8, divide it in half, and then I subtract 1, I get 3. Right, so I've divided the number of ones in half, right, by, the power position's at 4, and now it's at 3. Right, so the other way to do that is with our conjecture. 3n plus 1 divided by 2 gives us the same results as this. So here are the two formulas that I'm basically taking the number and starting at it and going up 2 steps, 3 steps, and then reversing that, right? So I'm taking the number 4, right? And when we are at the number 4, we're going to divide by 2 and then divide by 2 again. So in essence, we're going to divide that number by 4. Right, that gives us half of the loop. The other half would be, if it's an odd number, we're at 1, we're going to multiply by 3 and add 1. And so I've taken both of those formulas, put them together, and I'm doing it both ways. So I'm starting at 1, multiplying by myself, or I'm starting at 1 and going to multiply it by 4, and then subtract 1, divide by 3. So what you're going to find is that x can only be 1 in either of these formulas, right? No other number can solve both of those formulas, which means it's the only number that can loop, right? And so when I plug in the number 1, I get 1, right? And I can solve it for 5 if I change it to divide by 16. But I cannot solve the second formula. And then I can divide by 64 and make it solve for 21. But again, I can only go one direction. I can't go both directions. And so, like I've showed, right, if we multiply by 2 and we move a 1 bit from the power side to the, or from the remainder side to the power side, we are doing a 2x plus 1 on the power side. And I showed you some 3x plus 1s on the power side. And so now I want to look at some 5x and 7x numbers. And we're going to see the same things. So when I multiply by 5 and 7, on the power side of the number there is a 5x plus 1, 7x plus 1 that happens. Right? Most of the time when we multiply any number, the power side will do nx plus 1. 1 mod 4s cannot accomplish this. So any number that's 1 mod 4 will not accomplish the nx plus 1. All 3 mod 4 numbers will every time, and cut the remainder in half. So let's look at some of these. So 5 times 5 is 25. So I took 4 times 1 and made it 4 times 6. So 5 times 1 is 5 plus 1 is 6. 5 times 2 is 10 plus 1 is 11. 1 is 6. 3 times 5 is 15, and we get 16, right? 4 times 5 is 20 plus 1 is 21. 7 times 1 is 7 plus 1 is 8. 7 times 2 is 14 plus 1 is 15. 21 plus 1 is 22. And it works for even numbers. 4 times 1 is 4 plus 1 is 5. 4 times 2 is 8 plus 1 is 9. So the only numbers that cannot create a power and a remainder are these. So when I multiply 1 times 1 plus 1 is 2, 4, 8, 16, and then the numbers 3. So basically any number that gives us a number that only has 1 in the binary, right, which are all the powers of 2. And what you're going to see is that 1 times 3 plus 1, or 3 times 1 plus 1, right, is on the list. And like I said, all these are powers of 2. So just like 1 is a prime number, it's also a power of 2 to the power of 0. When you plug in 2 to the power of 0 into 3x plus 1, your result is 2 to the power of 2. So the 3x plus 1 fails to do its job on 2 to the power of 0, right? It's expecting to divide that by 2, and it can't because it's a 1. And so it, right, it's basically applying the wrong formula to that number. 1 doesn't fit either side, right? It's an odd number, so we're not going to divide it by 2, and it's an even number when we're looking at multiplying it 3x plus 1, so it doesn't it's incapable of handling that formula the way it's expected, which is applicable to half of all our odd numbers. So I showed you all this in a previous video, but I can take any number and look at it with a mod 8 perspective, right? I can mod 8 any number and it will give me the results. But what I want you to see is that both one mod 8 and 5 mod 8s are 1 mod 4 numbers, right? But these never change, right? They're going to be either 1 mod 4 or 1 mod 8. And then you have your 3 mod 4s that are divided into 3 mod 8 and 7 mod 8s. And the 3 mod 8s will always be 3 mod 8s. But on the 7 mod 8s, we have something that's happening, right? So we have 7 mod 8, and then we have 15 mod 16, 31, 32, and 63, 64, right? And so with 7 mod 8s, you have this thing that's happening where you're going up in size. So let's look at it. So you have 7 mod 8, 15 mod 8, 32 is going back to 7 mod 8, and then you have 31 mod 8 is a new number, and then you have 7 mod 8, 15 mod 8, or 15 mod 16, and back to 7 mod 8, and then we go up to 63. So we're going up to a new one. And all of these go to a number in the one below them. So a 63 will go to a 31, 31 will go to a 15, and a 15 to a 7. And so then you have to double it again to get your next one, 127. 127s go to 63s. And then the next level up, right, we're doubling it again to 255s, we'll go to 127s. 511s will go to 255s, and so on. Right, so all of these numbers go to the one below them. So what does that look like? Right, so if I take the number 7, multiply by 3 and add 2, I'm at 11, 17, 26. So I go 7 mod 8, 3 mod 8, 1. Right, but if I go up to the next level on those, right, the 7 and 1 stay the same, but 3 changes to 11. Right, and here we're going to look at all of those numbers that we just did. So 15 goes to 23, which is 15 to 7 to 3 to 1. Well, 7 changed to 23 when we went up, and 1 changed to 5. But 3 and 15 stayed the same. And as long as the 1 mod 3 number is a 2, then you're going to be able to add another odd number on the top side and keep going. So, right, our next number is 23. So 23 is a 7, but it goes to 15, right? So if I'm going in the reverse direction, I can only go to 15 from 23, right? Or I can double 23 to 60 or to 46. And so then the next one is 31, right? 31, 15, 7, 3, 1. And then, right, I'm taking those numbers and going up one mod level on them. And so 15 changes to 47, and 11 and 1. So the next one is 39. Here you see 47 is a 2 mod 3. And so it goes to 31 next, right? And 71 goes to 47, right? So you can see I lost my little arrow. So 71 is over here as well. I mean, that whole chain, right? You can't change those. 95 comes into 63. So once you hit a 0, right, you can't go to any other odd numbers. And if it's a 1, you're in 2 steps. You can only have an even number. Right, you can't have an odd number in 2 steps. So it can't continue this chain up. So there's 72, 72 goes to 47, 47 goes to 31. 119 is coming from another location. There it is. 119 is going to 79, and then 79 ends. So every third one can keep going another level, right? And every third one is a mod 0, so it's the end of the odd numbers. And every third one can go up to and find another odd number. And so there's 127. As you can see on our far right, we went from 31 to 63, back to a 31, then to a 127. So only our fourth column is doing something different, right? Our other 3 columns are going to stay 7 mod 8, 15 mod 16, 7 mod 8, right? So half of our odd numbers that are 7 mod 8s are going to be 7 mod 8s, so 50%. And so on the others, right, the rest of those, 50% of those are going to be 15 mod 16, right? So with what we have left, half of those are going to be 31, 32s, right? And then we go to 63s. Half of the remainders are going to be 63 64s. All right, so that's 6 ones at the end. 7 ones at the end is going to be half of the remainder. And so every level that we go up, so if we go up one more level, right, let's just draw this out. Our next level is 255. Only half of the numbers going forward are going to be 255. So now let's look at this a little differently. So all odd numbers are 1 mod 2. Right? And then we break them into 1 mod 4 and 3 mod 4. And all 3 mod 4s go to a 1 mod 4 number. So what do I mean? You take the number 3, you multiply it by 3, you're at 9, you're at 10. 10 divided by 2 is 5, right? So you go from 3 to the number 5. But we go from 3 to either a 1 mod 8 or a 5 mod 8. So looking at it from a mod 8 perspective, and then you have 7 mod 8s that go to 3 mod 8s. Right? Now if we go to mod 16, right, 11 mod 16s go to 1 mod 16s and 3s go to 5. And 7 mod 16s go to both of those. And we go up to 32, we can now break the 7s and 23s into where they go, right? 7 mod 32s go to 11, go to 1. 32s go to 3 to 5. And 15s go to both of those. And if we go up a new level, right? 74 goes to 7 and 15 goes to 23. And 3164s go to both of those. Right? And then if we go up a new level to 128, 31s go to 47 and 95s go to 15. And 63s go to both. Right? So the higher we mod a number, the more information we can tell about where that number is going to go. Right? And they never change. Right? So once we know the mod of a number, we know the path that it's going to go down because it cannot change. And so what's that look like when we're going through our numbers? So all 15 mod 32s are going to go to 7 mod 16s. 7 mod 16s are going to break into, right, 11 mod 16s and 3 mod 16s. 11s are going to go to 1 mod 8s and 3s are going to go to 5 mod 8s. And then we're going to loop back and find another number, right, with both 1 mod 8s and 5 mod 8s, right? We reset the loop, right? With a 1 mod 8, we're going to do a 4-2-1 loop. And with a 5 mod 8, we're going to just do a bigger loop. Now at some point, we're going to find a 5 mod 8 that's going to take us to the number 1, right? And keep in mind that to find the correct power position, we read the binary from right to left, find the first group of 1s, and the 0 after that is our power position. Right? And then we can dig into a number and get bigger loops. Right? That's the only thing that's going to happen as we get into larger numbers. But they're all going to fit into this pattern somehow. And then the only 1 mod 8 that can get to the number 1 is itself. So it has this independent loop because it's a 1 mod 8. And 1 mod 8s are the only one that can get to another odd number in 3 steps. So anytime you multiply a 3 mod 4 number, it does a 3x plus 1 on the power side of that number before you add 1 to the remainder side. All 1 mod 4 numbers cannot do this, so you get a 4-to-1 loop. So 50% of all odd numbers are going to give you a 4-to-1 loop. Right? So what is the difference when we have a 1 mod 4 number? We're doing a 3 times 1 on the power side. With 3 mod 4 numbers, we're doing a 3 times 1 equals 4 on the power side. And so let's look at all 8 possibilities, right? We're going to give you a number multiplied by 3 and then add 1 to it, right? So we're going to get the number times 3, the result, plus 1. So here is the number 1, right? It's a 1 mod 4 number. And as you can see that when we multiply by 3, nothing's happening. We're just pushing the power position from slot 2 to slot 3 to slot 4. Right? The plus 1 is having its impact on the remainder side. And so when we look at the number 2, we see the same thing. It's just pushing the power from slot 3 to slot 4. With the number 3, we have a 3 mod 4 number, and what happens is we have a 3x plus 1 happen when we multiply by 3. All right, our power position doesn't change. It's in the 0 slot, and it remains in it's in the 3rd slot, and it remains in the 3rd slot after we add 1. So we multiply by 3, we change the power of that number by 3x plus 1, and then we add 1 to the remainder side. 4 does the same thing as 2, right? We move the power position from 4 to 5. Uh, 5 is the same as 1. It's a 1 mod 4 number. But the power position is going to have a larger change, right? We're going from slot 2, and in this case, to slot 5, and then slot 6 after we add 1. So when we do the multiply by 3, we're not having as big of an impact on the power side as much as we're having on the remainder side with 1 mod 4 numbers. 6 has 2 1s on the remainder side, so it's going to act like a 3 mod 4 number, right? The power slot is in 4, and after we multiply by 3 and add 1, we're still in the same power slot of 4, but we've multiplied our power side by 3 and added 1. 7 is a 3 mod 4 number, so the power position will not change. Right, we're in 3 or in slot 4, and it's going to remain slot 4. And the only thing we're going to do is take a 1 from the remainder side and add it to the power side. And then the number 8 is just incrementing up from 4, so our power slot is going to start at 5 and go up to 6. Right, so after the number 7, the only thing that's going to happen is bigger 3 mod 4 numbers. And so just to show you these, like I said, all 1 mod 4s and 3 mod 8 numbers are going to be the same, right? When we multiply them by 3, there's not a change in our mods necessarily, but with the 7 mod 8s, you're going to see it's going to change. And the interesting thing is the 5 mod 8s and 7 mod 8s are going to cycle in and out of 16. So 5 and 7, you have 16, and 5 is 32. When we go to 13 and 15, the 16 flips to the 5 mod 8, and we get a new 32 on the 15. And so we'll alternate back and forth to 16 between those as we go up. But what you need to see is where I have 0 and 0, it's confirming that the power positions are the same and that the gray numbers are incrementing. So with the 3 mod 8, you're going to see we go from 0 to, we multiply by 3 and add 1, we get 1. It's going to increment by 1, so we go up to 1. 1 times 3 is 3, plus 1 is 4. 3 times 2 is 6, plus 1 is 7. So here 32 is we're back to 16. So the first one we have 0 to 1, and then we have 1 to 4. And then we have 64 in our, right, we're just going to be incrementing up with the 3 mod 8s, but the 7s are going to cycle in and out of new numbers. So here's a new one, 64, so 0 and 1. We're back to 16 for the third time, so 2 and 7. 32, 1 to 4. And this is our fifth 3 mod 8, so it's 3 times 5 is 15, plus 1 is 16. And so these are just, right, our 3 mod 8s are just incrementing by 1s, and every other one is a 16, and you can see we're up to 5 times 3 is 15 and 16. and then we have a new one, or 64 is the second time we have 64, so it's a 1, right? It's the second time because we started at 0. So anytime I have a 1 mod 3, I can use the formula to find a new odd path. So what does that mean? So now we're going to go back from the number 1 and see, we're going to path backwards to any number. So anytime I am at a 1 mod 3 number, I can apply this formula and shift right. Right, I can break out to an odd number. So 1 is capable of doing this, but every other number is going to be a 1 mod 3, so I can break out to 5. Right, so there's only one path to any given number. So let's look at the number 9, right? So when I start at number 1, I can break out at 4, but that's just going to send me back to 1. So I have to break out at 16 to 5. 5, I can break out to 3, but I can't go anywhere with that one. So I'm going to go up to 13. 13, my next breakout is 52 to 17. And I can break out, break out, break out, and then we're at 9. 1 again is going to loop. 1 is the only 1 mod 8 that can reach the number 1. Everything else is a 5 mod 8 number. So 5 is the next number that can get you to 1. So when we're talking about breakouts, right, I can only have 3 different 1 mod 3 results. I can have 0 mod 3, 1 mod 3, or 2 mod 3. Right? If I am 1 mod 3, then my first breakout can be a 1 mod 8 or 5 mod 8. So you can see this here. If I am a 2 mod 8 or 2 mod 3, then I can go from a 1 mod 4 to a 3 mod 8. If I'm a 3 mod 8, I can only go to a 7 mod 8. If I'm a 7 mod 8, I can only go to other 7 mod 8s. And second breakouts and above can only be 5 mod 8s. And 0 mod 8s cannot have a breakout. So for any 1 mod 3, I can use the formula to find all the odd breakouts. And our first one, number 4 sets the pattern for all of these numbers to use to make the breakouts. So 4 times x plus 1 equals, right? So I'm going to start with 0 and I get 1. And I'm going to take and plug in that result and get 5. 521, 85, 341, 1365, 54, 61. Right? The next odd number for all of these is the number 1. And this is the pattern, right? 1, 5, 21, 85, right? All other odd or even numbers are going to break out based on those specific numbers. They won't make up their own numbers. Right, so what's that mean? Right, I'm creating a base of 4 times 1, or 4 times these numbers plus 1 to get my breakouts. So 5 breaks out, 21 breaks out, 85. And you can see that I can break out on these numbers. And so here you see our next base is 10 and 3. And so 10 times 0 plus 3 equals 3. So I can break out 3. 10 times 1 plus 3 is 13. So I can break out on 13. 10 times 5 is 50 plus 3 is 53. So I can break out on the number 53. So I can use this formula to find all the breakouts for 10 and 3. Right? And the next one would be 5 and 16, right? But 5 and 16 are not a base, they're just following 4 and 1 at a higher level, right? So 16 times 1 plus 5 is 21, right? So they're just going to duplicate up 7 and what would that be? 7. Let's go find it. 7 and 22 would be the next one. And then 9 and 28, right? Yeah. 11 and 34. And then 13 and 40. 13 and 40 is going to be a copy of 10 and 3. All right, so our first breakout for each of these is our base, right? That gives us our breakout, it gives us where our breakouts are going to be for that level. And then I can go up here to the top of this one and break out, and there's my base for this huge number, right? But it's still going to be 1, 5, 21, 85, right? Our base above the number 1, which is 4 and 1, gives us the pattern to use to find every other number. And again, right, the first 1 mod 3 is the base for each of these shifts. So now I want to go from the number 1 to the number 27. Alright, so I have a 1 mod 8, I break out to a 5 mod 8, and then I break out to another 5 mod 8, and because I'm going 2 steps, I'm adding a 1 to my remainder side, so I am at 3 mod 8, and then I'm breaking out in 2 steps, so I'm going to a 7 mod 8. But I'm not going to 15, I'm going up to 61, so I'm back to a 5 mod 8. And I'm skipping the first one, so it's another 5 mod 8. I'm going to my first breakout, so it could be either 5 mod 8 or 3 mod 8, but because it's 3 steps, it's a 1 mod 8. 3 steps, 1 mod 8. And here we go up to our big 9,232. So we skip the 769, and so it's a 5 mod 8 breakout. But we're going to 2 steps, so we're at 3 mod 8, 2 steps to a 7 mod 8, 7 mod 8, and back to a 5 mod 8. Alright, when I go from a 1 mod 3 to a 2 to an odd 2 mod 3, I can keep adding 1s to my binary number. Right, but when I hit a 0 or a 1, I'm done. Right, those will be the last of the increments of 1. Right, so as long as it's a 2, I can keep adding a number to that. But so here we went from a 5 mod 8 to a 3 mod 8, and then we're going to do our 6, right, 319. So we did 3 or 6 steps of adding a 1 to the remainder. And then we hit 319, which is a 1 that ended, so we went back to a 1 mod 8 number. And so then we went to a 3 mod 8, but back to a 1 mod 8. 3 mod 8, 7 mod 8, and then we went to a 5 mod 8. Right, and you just see this happening over and over. And there's 31, so there's our 5-step number that this should be known for, but because of 319 is a 6-step, right, it made this number famous. Right, so we go from 31 to 41 to 27, and then 27 is a 0 mod 3, so we cannot go to any other odd numbers. Right, so from the number 1, we shifted right 41 times to reach the number 27. Right, and so just to look at these patterns, right, so 4x plus 1, 3x or 10x plus 3, 5 and 16, 7 and 22, right? 5 and 16 is not a base, right? It's a copy of 4 and 1. So you can see the same numbers in both of those. So here's our first 8 numbers, right? But you can use that formula to find your matches. Right, and so here's just a few more. Right, there's 319 and 958 is its even number. And let me pause this for a second. Alright, so let me bring this over and I want to show you this. So I can take, I've written a code, right? I'm going to put in the number 7, right? It's going to run through the steps of that number. It's going to tell me the correct power position of that number, right? And it's going to tell me I'm starting at the number 7. There's 16 steps. The trend is 3. So the highest cycles going up is 3. I go, I do 5 shifts and 11 divides. So I have 5 numbers that I multiply by 3 and add 1. And then I divide by 2 11 times. Is this number a base? So it knows how to check for a base, and it matches 4 and the C base is 4, but it's 7 and 22 is R. So what do I mean by the C base? Let me show you. So each number has basically it looks at the shifts and says the C base is 1 less. So the number 7 has 5 shifts, so it's 4 to the right of the number 1 base. So the 4 and 1, the base, it is 4 to the right of that. So 5 shifts to the right. Right, and so I can plot all those numbers on here, and none of them are going to have the same results, right? Every number is going to give me a different amount of steps, shifts, divides, and let me know if it's a base or not. Right, but I can type in any number I want, 27. Oh, I have to tell it to run the program, 27. And it's going to give me those results. There's 111 steps. It is a base, and it's 82 and 27, and then it's 41 shifts to the right, and its highest trend is 5. So 27, 41, and 31. Right, these 3 numbers, right, should all be a trend of 5, and 31 is the only number that has a larger trend in it than the trend it starts with. So 31 starts a 5-step trend. Right, so if we go up here to 31, 47, 71, 107, 61, 142. So it does this 5 steps up, right, and then it hits 121, and then in 3 steps, 121 is below itself. Or actually, 161 is a mod 4 number, and in 3 steps it's 121, but in 2 steps it's right a larger number, but because we're dividing by 2 times, we're below ourselves on that 3rd step. Right, but I can plug in any number and it will give me those results that we're looking at here. And then again, we're going to look at a couple of numbers. that we're going to look at the binary and the correct power of those. So the first number, we're going to start with the number 23, which is 10 ones on the remainder side and 0 in the power side. And so again, right, we're going to multiply with 3, add 1 for our first step, but on our power side, we did a 3x plus 1 to the power side, right? We went from 0 to 1. And we're going to divide by 2. So we've taken the remainder from 1023 to 511. So we've divided our odd remainder in half, right? We divided 10 ones to 9 ones, right? So when we have 4 is 1, 0, 0. When we divide by 2, we've divided the zeros in half, right? So we've divided the ones in half. Right, we multiply by 3 and add 1. On our power side, we went from 1 to 4, so we multiplied 1 by 3 and added 1 to it. Right? We divide by 2, right? We're not changing our power number, right? We stay at 4, but we divided our remainder from 511 to 255. We divided it in half. Right, multiply by 3 and add 1. So we went from 4 to 13. So 3 times 4 is 12, plus 1 is 13. So then we divide by 2. All right, we divided 255 in half. Right, and so we continue this process till we get to a, right, 7 mod 8s are going to go to a 3 mod 8. And here it is, right? When we get down to the 2 ones in the remainder, we're now at a 3 mod 8 number. And so here we're going to do the same thing, and we're going to get either a 5 mod 8 or a 1 mod 8. And in this case, we got 5, right? So we're going to, right, we're at a 1 mod 4. So on 1 mod 4s, we're going to do a loop reset, right? We're going to do a 4-2-1 loop or bigger. With 5 mod 8s, we're going to do a bigger loop. And so if you look, it's going to be, when we're reading the binary for 5 mod 8s, we're going to look from right to left till we match 2 zeros or 2 ones. And that is going to be where our 1 in our remainder side is going to start, right? So in this case, it's just 1, 1. So it's going to be at that last pair, right? And so we do a loop reset. And so now we're at 16, and since our remainders are even, we're going to divide, right? So we're going to divide 4 times. 1, 2, 3, 4. And we're at a 5 mod 8, so we're going to do a loop reset, but you can see we're going to do a large, right? We're going to take that remainder of 1 and push it out to the 512 spot, right? So here we go. See, it's at the 5. I guess I looked at it on the wrong. So 256. So we went from 2 to 256. And our power is in the 512. So now we're going to divide by 2 8 times. Right? And we get down to another 5 mod 8. but this one's going to be the smallest that we can have. So 101 is a 5 mod 8 number, and so since I'm matching the 1 right off the bat, right, this is the smallest loop we can have with a 5 mod 8. They can go to an infinite size, right, because we could go 1 0 1 0 1 0 as many times as we want, and until we match 2 zeros or 2 ones, that's where that 1 in the first slot is going to go to. Right, so in this case it went to the 4th slot, so we get a 3216 plus 8 number. Right, and so we're going to divide by 2 3 times. And here we get our first 1 mod 8. So the 1 mod 8, we're going to do a loop into a 421. Right, so we loop reset and we get a remainder of 4, remainder of 2, remainder of 1. And so we're going to do it again because we're at another 1 mod 8. So we're going to loop reset 4 2 1. And now we're at a 5 mod 8, so we're going to do a bigger loop. Right, and this time we got 3 1s in our remainder, so we're going to divide by 4 or by 2 4 times, and then we're going to have a 7 mod 8 number, right? 4 7 mod 8, 3 mod 8. So in 2 steps we're going to be at a 1 mod 4 number, right? In this case it's a 1 mod 8, 17, 26, 40, 20, 10, 5, and we do our last loop reset, right? 16, 8, 4, 2, 1, right? And so now we're at the number 1. We're going to do a loop reset, and again, since 1 is incapable of taking the remainder and moving it to the power side, right? The power shifts from slot 2 to slot 4, and we're going to loop, right? We're going to just keep that cycle going because there is nothing to give to the power side anymore. I have nothing, right? Up until that point, right, with 5, right, 5 is the last one that's, right, when I do 5 times 3 and add 1, I get 16, and so 16 puts me at a number that is, 1 bit. It's a perfect power, so now I'm done, right? I can't give anything to the power side anymore. I have 0. Once I have 0 on the power side and 1 on the remainder, right, I'm done. All right, so now let's look at the number 27, the one that fascinates everybody. And what's cool to me is that we start with 3 on the power side and 3 in the remainder. And the first 2 steps, we get to the number 41. Right, and so I want to just grab this real quick. So if we look at the number 27, our glide is 96. So when we come down here, it takes us 96 steps to get to a number below 23, which is below 27. But 41, right, if we put in 41 and calculate, we're below 41 in 3 steps. So our glide is 3. And, right, we get to 9,232 is our climb, but we're below ourselves in 3 steps, right? So from 27, we go to 41, and in 3 steps, right, we're at 31. So we're below 41 in 3 steps. So with all 1 mod 4 numbers, we're below ourselves in 3 steps, right? And all 3 mod 8s are going to go to a 1 mod 4 number. Right? And again, with 41, we did a loop reset into this 31, and 31 is 5, 1. So now we're going to climb 5 times, right? 1, 4, 13, 40, and then we do a loop reset, right? So we hit a 1 mod 8 and did a loop reset. So we do these loop resets when we get to a power of 4, right? And so in 3 steps we're at a 1 mod 8. Now we're at a 3 mod 8, so we're going to do a 2-step climb. So 91 to 1, or it goes to 274, and then 412, right? And then we're going to divide by 2 twice and get to 103. So in 3 steps, I'm below 137, right? So anytime you see a 1 mod 8 or 5 mod 8, we're below it in 3 steps. So that happens like 16 times in this number. So here we went 103 to 155 to 233. So in 3 steps, we will be below 233. Right, we do our loop reset, 700, and 175 is below 233. Right, so we're just from 27, right, we're just shifting left to these next columns until we get to the column with 4 and 1 in it. Right, so here we're going to do 4, right, and now we're going to do a loop reset, and in 3 steps we're below 593, right, and here we're at 445, and in 3 steps we'll be below. The only difference is if I'm going from 1 mod 8, I'm going to be at an odd number in 3 steps. With 5 mod 8, because we're doing these bigger loops, right, 3 steps we're going to be at an even number. So 1, 2, 3, right, we're below what were we at? 445, right, we're below that in 3 steps, but it's an even number, so I still have to go 1 more to get to the odd, right, and here we're at 167, and it's a 7 mod 8, so I'm going to go to a 3 mod 8 in 2 steps, and in 2 steps I'll be at a 1 mod 4 number. In this case it's a 1 mod 8, so we're going to be at an odd number that's less than 377 in 3 steps. 1, 2, 3. 283 is less than 377. So we're at a 3 mod 8, so in 2 steps we're going to be at a 1 mod 4. And this is a 1 mod 8, so in 3 steps we'll be at an odd number less than 425. We're at 319. 319 is 6 ones. And so we're going to go up 6 times. Right, so we're going to climb 6 times. Right, so we climbed all the way up to 4,858. We hit this 24, 29, and I guess it's going to go up to 7288, divide by 2, and now we're going to be at an even number that is less than 2429. Right, 1812 or 1822. Right, we're less than 2429, and now we're going to divide by 2 one more time. We get 911. 911 is going to go up 4 times to our favorite number, 9,232. But 3077 is a 5 mod 8 number, so in 3 steps, 2 more from 9232, we will be below 3077. Right, we're at 2380. So again, if I put in that number here, 3077, and say calculate, our glide will be 3, right? So we went to this 9232, it's our largest number, and in 2 steps we're at our glide. So everything's instantaneous because we're at our peak for the number 27, right? So we still have to divide 2 more times, and we're at a 1 mod 8, so we're going to do a loop reset of 4, 2, 1, right? 4, 2, 1. So all of these numbers were going lower, and then we hit a 5 mod 8, so we do a 16, 8, 4, 2, 1. So right, these loops are happening with 50% of our odd numbers, right, are doing these loops that we're so fascinated with the 4-2-1 loop, right? And you see on this screen we have 2 4-2-1 loops that happen. The only difference is we do not have a 0 on the power side, right? We have some type of power out there, right? So we're at 108, 81, 15, right? But these numbers are decreasing, right? The closer we get to the number 1, right? The power of that number is decreasing. So we're doing 4-2-1 loops, but it's 108, 4-2-1, 81, 4-2-1, right? And then we do a bigger loop, but it's 15, 16, 8, 4, 2, 1. So now we're going to do another loop reset, and this time we're at 56. So that means we're going to get a bigger than a 1 coming at us, right? So we have 3 ones together coming at us. So 14, we get to 7, right? We're at 7 mod 8 now. So now we're going to climb 3 times, right? And now we're at a 5 mod 8. So we're going to do a loop reset to 32, right? And it's a pure number, so it's 30, right? And it's a 1 remainder, right? So I'm going to the number 5, basically. All right? Because I only have 1 in my power side. So now I'm going to do my last loop reset. Right? I have nothing more to give to the power side. I have 0 and I only have 1 remainder. So now I'm stuck, right? So all I'm going to do is loop because I have nothing to give to my remainder side and all I have is a 1. So every time I get to the number 1, I'm going to do a 2 to the power of 0 times 3 plus 1, and that's going to put me at 2 to the power of 2. And so because all we have left is powers of 2, I'm just going to loop. So all 1 mod 8s fall below themselves in 3 steps. They follow this 4 to 1 loop pattern, right? So I start with 0, 1 as my binary, and I do a multiply by 3 and add 1. I'm going to be at 1, 0, 0 binary, and then I'm going to be at x 1, 0 binary, and then x 1 binary. Right? The number 1 is the only exception because you can never have a power strength bit. Right? The next 1 mod 8 is 9, and it's 1, 0, 0, 1. All 5 mod 8s follow the same pattern as above, right? Except they follow a bigger loop. So 8, 4, 2, 1, or bigger, right? 16, 8, 4, 2, 1. 32, 16, 8, 4, 2, 1, right? They're going to just be a bigger loop than what you have with the 1 mod 8. 1 mod 8 is going to be 4, 2, 1 every time. So every 1 mod 8 has a 3 mod 8 that can get to the same place in 2 extra steps. So 1 goes to 4 in 1 step. 5 gets you to 4 in 3 steps. Right? 3 goes to 10 in 1 step. 13 gets there in 3 steps. 5 goes to 16 in 1 step. 21 gets you to 16 in 3 steps. So every 1 mod 8 has a 5 mod 8 that can get to the same place in 2 more steps. So every 1 mod 8 has a 5 mod 8 pattern. All 3 mod 8s get to a lower number in 5 steps. Right? So in 2 steps they're going to be at a 1 mod 4 number, and then a 1 mod 4 will always be below itself in 3 steps. So in 5 steps a 3 mod 8 will be at the same number. So 27 is a 3 mod 8 number, and it's at 31 in 5 steps. Right, this will be the pattern for all 3 mod 8s. And then all 7 mod 8s will go to a 3 mod 8 in 2 steps. Right, if they're true mod 7, which is 50% of all 7 mod 8 numbers. Right, they'll be at that 1 mod 4 number in 7 steps. Right, so the example here is 553 will get to 40 in 3 steps. 35 will get there in 5 steps, 23 in 7 steps, and 15 in 9 steps. So all 1 mod 4 numbers equals 1 mod 8 and 5 mod 8 numbers. All 1 mod 8s fall below themselves in 3 steps. All 5 mod 8s fall below themselves in 3 steps. Right? All 3 mod 8s will be at a 1 mod 4 in 2 steps. 7 mod 16s will be there in 4, and so on. Right? Each time we add a 1 to the remainder side of the binary number, right, we're adding 2 steps to get to the number that will be below itself. Right? So I can keep going with this to all 7 mod 8 numbers. And let me see. So I want to show you this real quick. Let me pause it. All right. So someone's asked me about skipping numbers. And so I've written the script where I put in a number. I can skip a lot of the noise, right? So in this case, with the number 7, in 4 steps, I can get to the number 1, right? So 27, I can get to the number 1 in 27 steps, right? I can skip all these other numbers because I mean it looks at the binary of these numbers and knows what to do with that. So what does that look like? So if we look at the number 7, right, if I just mod 8 that number, you can see that on the left, right? There's all the steps, mod 8, what it looks like. And so then if you look at the second column shows the correct mods of those numbers. And so you can see that the only numbers that I can't skip are the mod 4 numbers. Right, so from 7 I can skip the next odd number because I know I have a formula that tells me if I'm not at a mod 4, you know, I'm at a mod 7, I know what that number between 7 and 17 is, right? I'm going to take 7, right? I'm going to take half of 8 and add that to it, which is 4. So 7 plus 4 is 11. 11 plus 6 is 17, right? So I know, looking at the number 7, right, I can look at the binary and I'm going to see that it has 3 1s. So I'm going to do 2 steps of adding half of the number that's right above me to itself. So I look at 7, I know I'm going to do that twice, so I just do that formula and I'm at 17. Right, 17, I'm at a 1 mod 8, so I know in 3 steps I'm going to be at my next odd number. And so I can skip all even numbers, right? I don't have to deal with even numbers. So I'm going to look at the, right, I'm at a 1 mod 8 number. So I'm going to look at the binary and say, okay, it's a 1 mod 8, so I'm going to multiply by 3 and divide by 4. Right, instead of dividing by 2 twice, I just divide by 4 and I'm at my next odd number. Right, so I'm just looking at the binary and cutting out the zeros. Right, and so I'm at 13. 13 is a 5 mod 8, so I know I'm going to divide by 8. Right, and so I'm at 5 mod 8 again, and this one's a 16, so I'm going to divide by 16, right? So it's looking at the binary of that number, and so basically I mod it till I find where the mods match, and then I multiply by 3 and divide, add 1, divide by that number. So I don't hit any of these even numbers. So in 4 steps I'm at 1, right, using that. And so for the number 27, right, I'm there in 27 steps. So you can see here that I cannot skip the where we're going to do a shift reset on the 4, on the mod 4 numbers. So they're highlighted in yellow. And so occasionally, right, we're starting with 27, it's going to go in 2 steps to the number 41. 41 is a 1 mod 8, so in 3 steps I'm going to be at my next odd number. And so it's a 7 mod 8, right? So 7, it's going to look at the binary and say, okay, there's 5 1s, so I'm going to do this calculation, and so I can skip to the mod 4 number, right? And so mod 4, I'm skipping the 2 even numbers, or I'm skipping, let me find a 1 mod 5, right? So here we have a 1 mod 5 number, so I'm skipping 3 even numbers, but I can skip all those even numbers. Anytime I have a 7 mod, I'm going to skip all the odd numbers to the last one, to the mod 4. Right, so I never have to touch these others. Right, and so I only have to do 27 processes to get to my number 1. And I did another number Right, this is a huge number. It has a ton of steps. All right, I think there's like 980 something steps here. Where's my R script? Let me grab this number. Right, so this number normally has 986 steps, right? Its glide is 29, so it's right off the bat, it's 29 steps in, it's below itself. But at some point, it goes higher, right? So the maximum number is right here at 111 steps. And then it just goes down to the number 1, right? But with using my formulas to skip a lot of those even numbers, right, I get it down to 240 steps. Right, and so here's what that looks like, right? We start off with this 7, it does a huge climb, right? And that step, it said step 29, right? So this step right here is the first number below it. But if we're honest with ourselves, we have all of these mod 4 numbers that are below themselves in 3 steps. So we have 5 other cases above it where we're below ourselves. Right, but as we continue along, you see here we skip a bunch of odd numbers, right, because we're just looking at the binary and I know I can skip those. But we do this, right, here's another one. As we continue down through this, we're just, occasionally we can't skip an odd number, right? I actually think I can get past those now with right, I'm working on a formula to go ahead and just go from 1, 4 to the next. That's not a very big one. There's a couple of huge, right? This has a 10 odd number climb, but it also has a huge even cut. We should be getting close to those. Right, so look at this number here, right? So in binary, this is 1 0 1 0 1 0 1 0 1 0 1 0 0, right? Something like that. So it just cuts all the, right, it just does this huge divide by 4096, right? So this number times 3 plus 1 divided by 496, and I'm right to this next number, right? So I can skip all of those even numbers. And then we get down here and we should find this one right here. So this number is a 10-step climb, right? 3071, right? Oh. So it's the second. 1023 is the first 2480 times 0 plus 1023, right? So this is the second instance of a number. So this number in binary is 1, 0, and then 10 ones, right? And so I'm just going to do 10 collapses to get to the 4. Right, and then we just continue 240 steps to the number 1. So, what happens when we divide these numbers? 2 to the power of 4 divided by 2 gives me 2 to the power of 3. Right, and so on. When I get to 0 to the power of 0 divided by 2, I can't do that. Right, I can't divide 1 in half. What happens when we multiply 3x plus 1 divided by 2 to these numbers? Right, 15 becomes 7, or 23, right? 7 becomes 2, 3 becomes 5, or 1. But when we do 1, right, it goes to 4 and then 2, right? The number 1 fills both of these. Right, when we're talking about this conjecture, right, if it's even, we're going to divide by 2, and if it's odd, we're going to multiply by 3 and add 1. 1 fails at doing either side of this, right? It should be dividing by 2, but because it's an odd, we don't try to do that. We plug it into the odd formula, and the odd formula is incapable of, right, we're trying to divide the number of ones we have in our remainder and give 1 to the power side. But when we do that with the number 1, it has nothing to give, right? It can't, it's giving itself to the power side, and when it does that, the power shifts. And so it can't perform, right? 1 doesn't accomplish what it should with either of these two formulas. So the number 1 loops, right? No other number will loop because there's a path that we can calculate to it and from it, right? And there's no diversion from that path, right? So when I plug in those numbers, right? When I plug in the numbers into here and get my shift divide and my base, how many steps, there's no two numbers are going to have right, look at 20 and 21 on here, right? They have the same steps, the same shifts, the same divides. Neither one of them is a base, but we know 21 is going to go to an even number, right? We know where it's going. 20 is going to divide by 2, right? So we're going to calculate those. So these appear to have the same calculations, but we know 1, right? They're both shifted over 1, but we're shifting from 5 and 21, right? So we're shifting at different numbers, right? So I'm doing all my multiplies by 2 up to 21, and then I shift over for the 21. With 20, I'm going up to 5, I do my shift, and then I multiply 5 2 times, right? But I know I'm going to, because there's an even and an odd, that 1 I'm going to multiply by 3 and add 1 and get to 64, and the other one I'm going to divide by 2 and go to 10, right? So they both have a place. So if I do a sort, right, and I say sort by steps and then sort by shifts, lowest to largest, right, that puts these two here, and if you look, 20 goes to 10 and 21 goes to 64, right? So they're different, right? We see that change. They look the same here, but they change at the next level, right? And 64 goes to 50, right? 50 goes to 40. Where's 5? 51 goes to 40. So both of these go to 16, right? So you can see how these numbers all are tied together, right? So there's no two numbers. Oh, and you might find, let me just click off of that. Let me show you this. So if you look at, and I can only calculate this up to Excel's capabilities. If you start with the number 1, right, it only climb, right, 1 goes to 4 and then to 2 and then back to 1. So its climb is 1. 3 goes to 10 and then to 5 and then to 16. So it climbs twice. So each of these, right, climbs an extra step. The only exception is 31. 31 starts out climbing 5 times, but it crosses 319, which is a 6, which is larger than 31. So it's the only one that I know of that has a larger climb within it than its initial climb, right? Each of these numbers right out of the gate climbs, right, an additional step for each one of these, right? They're the first ones to do that climb. 31 is the smallest number that does a 5-step climb out of the gate, right? It's the smallest one. 27 and 41 are tied to it, right? So 27 is actually a smaller number than 31, but 31 is the climb, right? That's where the climb starts and goes 5 steps up. but then it cycles around and hits 319, and that one goes up 6 steps. But 63 is the first 6-step climb out of the gate, right? So these powers of 2 minus 1 give us our first number that can do that climb. And again, when we're looking at these numbers, all odd numbers are going to be, 1 mod 2. And then half of them will be 3 mod 4. Half of, well, half of all numbers will be 3 mod 4. Half of 3 mod 4s will be 7 mod 8s. And then it's going to half continually, right, up to whatever number you want to go. But you're more and more less likely to run across a number with more than 6 ones in it, right? Your odds of a number having more than 6 in it decreases significantly after 63, right? Because it's just hard. I mean, it's easier to find a 1 mod 2 than it is to find a 3 mod 4. But I thought it was interesting that 30, this 31's the only one that breaks this number. But again, I can only check in Excel or in R up to 2 billion. After that, you start getting errors. All right, to look at numbers larger, I go to the website that you see on your screen, right? And I've done numbers up to the power of 200 minus 1. So you put these in here and they will calculate out any number that you want. And then for the wheel, I use this website. So what it comes down to is 1 is the only odd 1-bit number that cannot split itself into both sides, the power slot, and thus just keeps looping 4 to 1. Thank you for taking the time to watch this video.